Hello students, welcome back to Jce Connect. We are discussing module 4 and today we are going to have the lecture 4 of this module 4, and in today's class we are going to discuss about negative feedback amplifiers. In the previous class we have discussed basic things about the feedback. That is, we have studied what is feedback. That is a process of giving fraction of output energy back to the input. Then we discuss about two different types of feedback called positive feedback and negative feedback. Positive feedback is also called as a regenerative feedback and negative feedback is called as degenerative feedback. So we have seen a quick comparison between the positive and negative feedback, and then in detail we have discussed about what is negative feedback amplifier by considering its basic block diagram as shown here, and then we have derived the voltage gain of a negative feedback amplifier, which is given by AF equal to A by 1 plus A beta, and from this we have seen that the gain of the negative feedback amplifier decreases with negative feedback, and also we have listed out other properties of the negative feedback. So today's class will be continuing with what are the different types of negative feedback amplifiers, and we are going to discuss one important type of negative feedback amplifier in your syllabus, and then at the end of this lecture we'll be discussing about some of the properties of the negative feedback we have listed out in the previous class. So we'll try to elaborate on those properties of the negative feedback. So we'll start with the different types of negative feedback amplifiers. So the feedback amplifiers we can classify into four different types depending on how the output sample is taken and how the feedback signal and the input signal are mixed at the input. That is, according to mixing and sampling employed, we can classify the feedback amplifiers into four types. Those four different types of amplifiers are called as voltage series feedback amplifier, current series feedback amplifier, current shunt feedback amplifier, and voltage shunt feedback amplifier. In brief, we will discuss like all these four different types, means what exactly these four different types of feedback amplifiers, and in your syllabus we are going to discuss only one out of these four types, that is voltage series feedback amplifier. So before we discuss about voltage series feedback amplifier, just quickly we'll see what are these different types of feedback amplifiers. As I said, depending on how the output is sampled and it is mixed with the input, we have these four different types of feedback amplifier. So the voltage series feedback amplifier uses output voltage. That means the feedback signal is taken in parallel with the output signal and it is connected in series with the external input signal. So mixing is series, whereas output is obtained across the load. That's why it is called as voltage series feedback amplifier. Voltage means output voltage is taken as the feedback signal and given to the feedback network, and whatever output we get from the feedback network, that is connected in series with the external input signal. So that is called as voltage series feedback amplifier. Then the second type is current series feedback amplifier. Now again here you can see that output quantity is current. So output current is taken as a feedback signal, it is given to the feedback network, and output of the feedback network is again connected in series with the source input. So it is called as current series feedback amplifier. Similarly, what should be the current shunt feedback amplifier then? Here again the output current is taken as a feedback signal, it is given to the feedback network. Output of the feedback network, what we get, is connected in parallel with the input signal. That's why it is called as current shunt feedback amplifier. And the last type is voltage shunt feedback amplifier. So here again we are taking output voltage as the feedback signal given to the feedback network, and output of the feedback network, what we get, is again connected into what? Connected in parallel with the external input signal. So it is called as voltage shunt feedback amplifier. I hope the difference between these four different types of feedback amplifier is clear. So we have four different types of feedback amplifier, and as I told, in your syllabus we'll be discussing only one that is voltage series feedback amplifier. So we'll see now what exactly this voltage series feedback amplifier. So already I have told you what do you mean by voltage series feedback amplifier. Here output voltage is taken and it is given to the feedback network, and the output of the feedback network is connected in series with the source input or the external input. That negative feedback amplifier is called as voltage series feedback amplifier. So we'll see what is the block diagram of it. See here, this is the block diagram of voltage series feedback amplifier. Again, it is a very important block diagram from your examination point of view. So you can see here we have considered an amplifier with gain A. There is a feedback fraction or feedback circuit with feedback fraction equal to beta. This is the source input V in, and we have the load resistance RL, and across RL we get the output V0, and that output V0 is connected as a input to the feedback network, and whatever the feedback signal we get VF, which is equal to beta times V0, you can see it is connected in series with the external input. And if you see the polarities here, how are the polarities of the input that are connected here? If you see that this is positive and negative, whereas the feedback signal here, VF here, this is negative and this is positive. That means this input signal and feedback signal, they are out of phase, hence it ensures that there exists what? Negative feedback, right? So we have to derive the expression for voltage gain of this particular amplifier. Like the block diagram, if you see, it is almost similar to the general block diagram of a negative feedback which we have discussed in the previous lecture. So the derivation again remains same. So here also we can show that the closed loop gain of a negative feedback, that is voltage series feedback amplifier, is again AF equal to A divided by 1 plus A beta, where A is the open loop gain and beta is the feedback fraction. So let us do that derivation once again quickly here, right? So we will be considering an amplifier with open loop gain A. So what is A? Output by input, actual input applied to the amplifier. V0 is the output and Vi is the input given to the amplifier. So the open loop gain of the amplifier A is given by V0 by Vi. Similarly, if you consider beta as the fraction of the output fed back to the input, then the feedback signal Vf is given by beta times V0. And the other, already I told you, Vin is the source input, Vi is the input to the amplifier, V0 is the output, Vf is the feedback signal or feedback voltage, and beta is the feedback fraction. Now, if the open loop gain A is V0 by Vi, then the gain with feedback, that is AF, is given by AF equal to V0 by Vin. Now, we have to write what is V0, what is Vin from this block diagram. We have to obtain the ratio of V0 by Vin, and we can get what is the closed loop gain of voltage series negative feedback amplifier. So from the block diagram, since there is a negative feedback, the effective input applied will be the external input Vin minus the feedback signal Vf, that is Vi equal to Vin minus Vf, because of the negative feedback. If it is a positive feedback, we would have written Vi equal to Vin plus Vf. Since here we are using negative feedback, we can write it as Vi equal to Vin minus Vf. But we know that the feedback signal Vf is beta times V0. So if you substitute this here, it becomes Vi equal to Vin minus beta times V0, and if you rearrange, you will get Vin is equal to Vi plus beta into V0. So now we will substitute this in equation 1. What is our equation 1? V0 by Vin. So we will retain V0 as it is, and in place of Vin, we will write it as Vi plus beta into V0. So we get AF equal to V0 divided by Vi plus beta into V0. Now we will try to rearrange this term. The Vi from the denominator, if we take common, it becomes Vi into bracket 1 plus beta into V0 by Vi. So this can be written as V0 by Vi divided by 1 plus beta into V0 by Vi. And what is V naught by Vi. You know that V naught by Vi is what? It is the open loop gain denoted by A. So if you substitute that A here, we get AF equal to A divided by 1 plus A beta. The same like expression which we have derived for general feedback amplifier, we are getting the same for voltage series negative feedback amplifier. So the gain of voltage series negative feedback amplifier, which uses open loop amplifier with open loop gain A and feedback fraction beta, is given by AF equal to A divided by 1 plus A beta. So what you can see from this, again the gain decreases by a factor of 1 plus A beta. Now here the product A beta will be normally much greater than 1. Therefore, if you neglect 1 in the above equation, or if you write 1 plus A beta is equal to A beta, the expression becomes AF equal to A by A beta, or AF equal to 1 by beta. So what you can see from this, it may be seen that the gain now depends only upon the feedback fraction beta and is independent on open loop gain A. That is, the closed loop gain of voltage series feedback amplifier entirely depends on beta. Thus, negative feedback provides high gain stability because the closed loop gain doesn't depend upon open loop gain A of the amplifier. Right. Now we'll be discussing some of the important parameters of the or properties of the negative feedback amplifier for voltage series feedback amplifier. Now the first important parameter is the input impedance. Now what do you mean by input impedance? The impedance seen into the input terminals of the amplifier is called as input impedance. So if you have this, if you see from here what is the impedance, this if you write it as Zi without feedback, and with feedback we can write it as Zif. So now we'll try to find what is that relationship between Zi and Zif for the voltage series feedback amplifier. So if you write input impedance of the amplifier without feedback as Zi and with negative feedback as Zif, now we have to write what is the relationship between Zif and Zi. Now if you see the input side, the feedback signal is connected in series with the source input or the input signal, and you know that always the series connection increases the resistance or the impedance. Thus, when negative feedback is used in voltage series feedback amplifier, since the input is connected in series with the feedback signal, the input impedance of the amplifier increases by a factor of 1 plus A beta, and therefore Zif becomes Zi into 1 plus A beta. It is multiplied by a factor of 1 plus A beta. Hence, there is an increase in the input impedance, which is one important property of the voltage series feedback amplifier. Now next, we'll see what about the output impedance. Now if you go back to the output circuit, output side of this block diagram which I have shown, now we have to find what is the output impedance here. Now if you look into the amplifier from the output side, you can see there is a parallel connection. That is, the feedback signal is taken like across the load, and because of that the feedback signal and the output signal, there is a parallel connection existing at the output. So easily we can write what is the expression for output impedance. That is, if we consider Z0 as the output impedance of the amplifier without feedback, and Z0F or ZOF is the output impedance with feedback, then as the feedback signal is taken in parallel with the output signal or the load, what happens when there is a parallel connection? You know that the resistances or impedance will, effective resistance or effective impedance will decrease. And since the feedback signal is taken in parallel with the output signal, the output impedance with feedback decreases by a factor of 1 plus A beta. Therefore, we can write the output impedance of voltage series negative feedback amplifier ZOF equal to Z0 divided by 1 plus A beta. So one simple thing you should remember here, wherever there is an increase, you should write the quantity without feedback into 1 plus A beta. And whenever there is a decrease, you should write the quantity without feedback divided by 1 plus A beta. That's why we have written ZIF equal to ZI into 1 plus A beta, whereas ZOF is equal to Z0 by 1 plus A beta. Third important parameter is bandwidth. Again, consider BW is the bandwidth without feedback and BWF is the bandwidth with feedback. Then you know that negative feedback decreases the gain of the amplifier. And since negative feedback decreases the gain of the amplifier, but the figure of merit of the amplifier called gain bandwidth product should always remains constant. And since gain bandwidth product should always remains constant, decrease in the gain should be compensated by what? Increasing the bandwidth. Hence, negative feedback amplifier should increase the bandwidth by a factor of 1 plus A beta. Hence, bandwidth with negative feedback in voltage series feedback amplifier is given by bandwidth with feedback equal to bandwidth without feedback into 1 plus A beta. So here we have seen that bandwidth increases by a factor of 1 plus A beta, right? So the effect of the negative feedback on gain and bandwidth is as shown in this frequency response. This is a frequency response of an amplifier. A frequency response is nothing but it is a plot or graph of gain versus frequency. So when you plot gain versus frequency, you can see that A0 is the gain of the amplifier without feedback, and normally the bandwidth is obtained at the cutoff frequencies, and the cutoff frequencies are taken 70.7% of the maximum gain, or 1 by root 2 times the maximum gain. So in this gain, this is the frequency response of the amplifier without feedback, where it is having A0 as the maximum gain, and 0.707 times A0 gives the two cutoff frequencies, that is F1 and F2. So here you can see that the gain is more and the bandwidth is less, right? So gain is more and bandwidth is less. Now if negative feedback is applied, then what happens? You can see here the gain has decreased, that is AOF, that is gain, maximum gain with feedback. And since the gain is decreased, you can see here what happens? Bandwidth will increase. So this frequency response clearly illustrates what is the effect of negative feedback on gain and bandwidth of the amplifier. Then the last concept in this voltage series negative feedback amplifier is how to prove that the gain is stable in negative feedback. Now in order to show that the gain remains stable in negative feedback amplifier, we'll consider the gain of the negative feedback amplifier is given by AF equal to A by 1 plus A beta. Now what we do is we'll differentiate this equation with respect to the open loop gain A. So if you do that, we get D by dA of AF, or dAF by dA is equal to D by dA of A by 1 plus A beta, right? So you have to differentiate A by 1 plus A beta. If you use that U by V rule or directly formula, trigonometric formula, if you use, it can be written as differentiation of A by 1 plus A beta as 1 upon 1 plus A beta the whole square. It is like d by dx of x upon 1 plus ax. Differentiation of x upon 1 plus ax with respect to x can be written as what? 1 by 1 plus ax the whole square. The same formula, trigonometric relationship we have used here, and we have written dAf by dA equal to 1 divided by 1 plus A beta the whole square. Now we'll try to rearrange this term. What I do is I will multiply and divide this equation by A so that its value will not be changed. So I will write A divided by 1 plus A beta. Out of 1 plus A beta square, I have written here 1 plus A beta. So another 1 plus A beta remains. So I will write that multiplied by 1 divided by 1 plus A beta. And since we have multiplied by A here, I am dividing it by A. So I have not changed this equation. The value of this particular expression remains 1 divided by 1 plus A beta the whole square only. Then you may ask why I have written like this, because now if you see this equation closely, we have got here a term called A by 1 plus A beta. And what is A by 1 plus A beta? We know that it is the gain with feedback, that is AF. So we can write this equation dAF by dA is equal to AF by 1 plus A beta into 1 by A. Now rearranging the term, I'll take this AF this side, it becomes dAF by AF is equal to dA by A into 1 divided by 1 plus A beta. This is the equation, dAF by AF equal to dA by A into 1 divided by 1 plus A beta. So what you can see from this equation, the rate of change of gain with feedback is less than the rate of change of gain without feedback by a factor of 1 plus A beta, because here we have dAF by AF, here we have dA by A, but the dA by A is multiplied by 1 plus A beta, hence obviously this quantity dAF by AF is less than dA by A by a factor of 1 plus A beta. So this equation shows that the relative change in dA by A in the basic amplifier is reduced by a factor of 1 plus A beta in the relative change of dAF by AF in the overall gain of the feedback amplifier, which shows that the gain is more stable in negative feedback amplifier. Right? With this, we close the discussion on negative feedback amplifier. So if you have any queries, you can contact me. Thank you.